So shall we start? A very good afternoon. So Pujita, Shanmukha, tell me where were we? What was the last topic? I think we were doing BA-CPR theory. Yes? Yes, Shanmukha, am I audible?
Yes, sir.
Yes, tell me. So we were doing BA-CPR, right?
Yes, sir. Yes.
Okay. So let us practice a few of the questions and then we'll continue with the class with a new topic. Which of the following is molecules is planar? NO3, NCl3, BH3, Tell me. A very good afternoon. Yes, tell me. The hybridization of atomic orbitals of nitrogen in NO2 plus, NO3 minus, and NH4 plus respectively the hybridization of atomic orbitals of N in NO2 plus, NO3 minus and NH4 plus respectively are. Tell me the first one. Which of the following molecules is planar? Tell me. A, NF3. Okay. What about others? Reshma, Avni, D. Okay. Shanmukha, Reshma, Avni. D as the answer. Okay. Yes, it's D as the answer. Because Sheetal, these are pyramidal in shape. Remember, just like NH3 we have these are pyramidal. BF3 is trigonal planar. Trigonal planar. And this is also just like this. So we have, because this also belongs to the nitrogen family, so BF3 is planar molecule. Then over the second one, the hybridizations of atomic orbitals of nitrogen in NO2 plus, NO3 minus and NH4 plus are respectively are. Tell me. Yes, tell me. Yes, NO2 plus, NO3 minus and NH4 plus respectively are? Tell me. Where it is SP, where it is SP2, SP, SP2 and SP3. Okay. So Sheetal is saying it is SP here in NO2 plus, SP2 and it's SP3. Yes? Is there anyone who is getting a different answer? This is absolutely correct. We have nitrogen is sp hybridized in NO2 plus, sp2 hybridized in NO3 minus, and sp3 hybridized in NH4 plus, ammonia. Good. Good. All right. So we wrapped up VSEPR theory, right? Now today we are going to start with a new theory, that is valence bond theory. That is valence bond. Now see, first of all, so basically how a covalent bond is formed. How a covalent bond is formed. So this theory says that suppose we have two atoms, atom A and atom B. It is having an atomic orbital. It is also having an atomic orbital. And suppose these atomic orbitals are half filled. These atomic orbitals are half filled. Then overlapping of these atomic orbitals take place. Okay. So overlapping of these atomic orbitals takes place, and I say that these atomic orbitals, the overlapping takes place and there is a formation of a bond. And there is a formation of a bond. So if I ask you how a covalent bond is formed, it's simply that atomic orbitals overlap. Yes, atomic orbitals overlap. The half-filled atomic orbitals of the valence shell. Let me write it. Half-filled orbitals. Half-filled atomic orbitals of the valence shell. Of the valence shell overlap to form a covalent bond. To form a covalent, and obviously these electrons I have shown with opposite spins. Okay. Tell me if this is clear. Tell me if this is clear. Yes? Clear? Alright. Now, now there is another condition. Like for example, I am considering these two atoms only, A and B, and suppose now I am saying that A is having an atomic orbital which is empty. A is having an atomic orbital which is empty, and B is having an atomic orbital which is filled. I mean, it is having 2 electrons. So here also I will talk about the formation of a bond, and here also I will say that overlapping of these atomic orbitals will take place and a bond is formed just like this. But yes, the way of formation of this bond is different. There it was the mutual sharing of electrons. Here it is the sharing of electrons, of both the electrons, by one atom to the another. And you know what kind of bond formation is this? This is basically a covalent bond formation. Sorry, a coordinate bond formation, which is also a type of covalent bond. Coordinate bond bonding, a special type of covalent bonding. Coordinate bond, a special type of covalent bond. Tell me if this is clear. Tell me if this is clear. Yes, Sheetal, which one? The star mark point. Okay. So Sheetal, I am saying that the half-filled atomic orbitals of the valence shells overlap to form the covalent bond. These two atomic orbitals, they just overlap to form a covalent bond, just like this. And I'm saying that there is a bond formation. But we can have another possibility also, where an atom A is having an empty atomic orbital and atom B is having the fully filled atomic orbital. Then B can share its electrons, both the electrons with A, and this type of bond formation is basically coordinate bond formation or a native bond formation. But yes, you need to remember one thing, that I am talking about covalent bonding, coordinate bonding only when I discuss the way of the formation of a particular bond. I mean how a particular bond is formed. But once the bond has been formed, you won't be talking about whether it is a coordinate bond or a normal covalent bond. I hope you are getting my point. Yes, once the bond is formed, it's a bond. You won't be talking about that it's a normal covalent bond or it's a coordinate bond. Once a bond is formed, it's formed. It's a bond now. So we are talking about the coordinate and normal covalent only till the time when we discuss that how a particular bond is formed. Okay. All right. Tell me if this is clear. Yes, Ankit, Avni, tell me if this is clear. B is sharing to A. Yes, B is sharing to A. Yes. Now see. Now when I talk about the types of bond formation, types of bond. So basically bond can be formed by the overlapping in two manners. First of all, overlapping of atomic orbitals. Overlapping of atomic orbitals along the internuclear axis, and overlapping of atomic orbitals above or below the internuclear axis. Above or below the internuclear axis. Okay. Now suppose I am talking about s orbital. This is my s orbital. Okay. This is the nucleus, and this is my internuclear axis. That is an axis that is passing through the nucleus. So this is my internuclear axis. If the internuclear axis is given in the question, then obviously you will take that axis as the internuclear axis. But if it is not given, then by default you consider z axis to be my internuclear axis. Okay, z axis to be my internuclear axis. So suppose this is z axis, and this is my s orbital. So suppose I am having an s orbital, take it, and I am having another s orbital, and this is my internuclear axis. Take it. So I'm talking about that they are approaching towards each other. They are approaching towards each other. This is my z axis. Okay, and this is also s. This is also s. So they are approaching towards each other, and they are overlapping. They are overlapping. This is their overlapping. Their overlapping leads to the formation of a sigma bond. Leads to the formation of a sigma bond. Tell me if this is clear. So if the overlapping is taking place along the internuclear axis, then in that case it's a head-on overlapping. It's a basically head-on overlapping. Head-on overlapping. This is both the sigma bond. Okay. And what is this? And what is this overlapping region representing? This overlapping region. This is the overlapping region. This shows that this is basically. This means that the electron density is maximum in this region. Is maximum in this region. Tell me if this is clear. Yes? Tell me if this is clear. So this is your head-on overlapping, and the overlapping region means that there is an electron density in this region. Okay. All right. All right. Now, suppose I'm considering this axis to be my internuclear axis, that is Z axis, and this time I'm talking about px and px approaching. This is another px. They are approaching towards each other. Okay. That I'm talking about this. This is my overlapping. Now this overlapping is obviously above or below the internuclear axis, and in this case there is a formation of a pi bond. There is a formation of a pi bond. I can also call it lateral overlapping, lateral or sideways overlapping. Sideways overlapping. Tell me if this is clear. Lateral or sideways overlapping. That means the electron density is more above or below the internuclear axis, just like this. Suppose this is my internuclear axis, and the electron density above and below is more. And these are my two nucleuses. Tell me if this is clear. This is just like this. Yes? Tell me if this is clear. That the electron density is more above or below the internuclear axis. I hope this is clear. Tell me. And this is head-on overlapping, or I can also call it axial overlapping. Axial overlapping. Alright. Okay. So suppose if I say that alright. Now there is a trick to remember what kind of bond will be formed. A trick to remember. See, so suppose there is a one loop interaction. There is a one loop interaction, or you have one loop overlapping. It will lead to the formation of a sigma bond. It will lead to the formation of a sigma bond. Like we have S, it is one loop only. It is also S, one loop. So one loop and one loop, it results in the formation of sigma bond. So can I say that S orbital can never form pi bond? S orbital can never form pi bond. Yes, tell me.
Yes, sir.
Any problem if I say like this? Can never form pi bond. Okay. And for obvious reason, because if you try to form the pi bond, this is my S. Suppose this is, I am showing with plus, that means the phase. And this is P overlapping with this. So this is plus, this is minus. So whatever there is a collective or what you constructive overlapping within the same phase, there is destructive overlapping also. I mean of the same intensity. So obviously it gets cancels out and there is no bond formation. So there is no bond formation. No bond formation, or you can also say zero overlap. Zero overlap. Alright. And whenever there is a two loop interaction, there is a formation of a pi. And suppose there are four loop, like for in the case of d orbitals, then there is a formation of another bond which is delta bond. But this is not in your syllabus, but yeah, for the sake of knowledge. This is the thing. Now P and P, you know that there are two loops. P and P, there are two loops, so obviously there is a formation of a pi bond. There is a formation of a pi bond. And what about four loop? Like for example, if you have something like this. Suppose in one plane I have this, and in another plane I have another d orbital like this. Check it, another d orbital like this. So basically, this overlap with this with this, this with this, and this with, and this with this. So this is a 4-loop interaction or 4-loop bonding resulting in the formation of a delta bond, just for the sake of knowledge. Tell me if this is clear.
Yes, sir.
That means PP bond will always be pi bond.
Which one?
PP bond.
Yes, obviously. When we have two loops, so obviously we will be talking about, it can't form delta bonds. Ankit, even if you form a bond like this, like P and D, then this is also a pi bond. Whenever there is a two-loop interaction, there has to be a pi bond. Okay?
Yes, sir.
Okay. Next. Now suppose if I am talking about that we have S and Px approaching along the x-axis. Can you please tell me what kind of bond will be formed? S and Px approaching along the x-axis. I mean they are approaching towards each other along the x-axis. Can you please tell me what kind of bond is formed? A sigma bond. So this is my x, this is my x, this is my s, and obviously Px. This is just like this. So there is one loop interaction, absolutely correct. There is one loop interaction, and this is called, suppose this is plus, this is minus, then there is a formation of a sigma bond. Absolutely correct. Absolutely. Now suppose if I am talking about Px and Px approaching along x-axis, can you please tell me what kind of bond is formed? Can you please tell me what kind
Sigma.
Sigma bond. This is a Px. This is also Px. And internuclear axis is along that is passing through the nucleus is also along the x-axis. Absolutely correct. This is also a sigma bond. Absolutely correct. Next, Px and Px approaching along y-axis. Tell me. Px and Px approaching along y-axis.
Pi.
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 This is your y-axis. This is Px. This is another Px. And there is a formation of a pi. Absolutely correct. Px and Py approaching along z-axis. Tell me. Approaching along z-axis. Tell me what it is. Approaching along z-axis.
Sir, no bond.
No bond. Why?
Sir, no overlapping will take place.
No overlapping will take place. Yes, what about others? Pi, pi, pi. So it is basically you have a z-axis. Suppose this is my px and this is my py. So obviously there is no overlapping that is taking place, because for this there has to be something like this, there should have been something like this so that this could have overlap, and for this there should have been something like this so that this should have overlap. Okay, but since they all are mutually perpendicular to each other, so there is no bond formation. Tell me if this is clear. Zero overlapping. Tell me if this is clear.
Yes, sir.
Is it clear? Okay. Next. So now we will discuss the strength of bond. Strength of bond. Or we can also say extent of overlapping. Effective overlapping. For effective overlapping, what are the factors? Now, first one is the small size of atomic orbit. Atomic orbit. For example, 1s and 1s is undergoing effective overlapping as compared to 2s and 2s. Now, I do not have to tell you the reason, only you will tell me the reason. So I am saying that in the case of 1s overlapping is stronger than 2s overlapping. Can you please tell me why?
1s orbital is small because its principal quantum number is small.
Yes, so what happens due to that? So basically, can I say that in the
more overlapping?
Yes, more overlapping, and can I say that more electron density in the overlapping region? Yes, tell me.
Yes.
And look here, less electron density in the overlapping region, and as the size increases, this thing goes on. And the second thing is, less diffused the orbital, more effective overlapping. Okay. For example, I have a p orbital. It is less diffused, and I have a d orbital. It is more diffused. Now, what is meaning of diffuse? Diffuse means the electron density is spread over a larger area, a larger space. So in D, it is more diffused as compared to P. So can I say that in P there is more effective overlapping than D? Yes? Tell me. Because the electron density is spread over a larger area. Here the electron density is spread over a smaller area. It is less diffused. It is more diffused. And F orbitals are further, they are even more diffused than the D orbitals. So can I say the F have even lesser effective overlapping than D? Yes? Tell me.
Yes, sir.
Okay. So if this is the case, I am giving you certain things. Like for example, okay, so this is about effective overlap. Now when I talk about the strength of bond, so basically you need to remember 2 points. Okay, so if you are having different shells, then here you will consider the predominant factor is size. Okay. And if you are having the same shell, then this is the order. P is more than S, more than D, and more than. This is what experimentally has been found. This is the experimentally found order. Now why? Because एक reason ये भी because P is directional in nature. Like for example, if I'm talking about the overlapping, I have this particular region to be to form the, to get the overlapping stuff, right? And this is my overlapping region. Whereas in the case of S, this is non-directional. It is symmetrical and non-directional. So overlapping can take place from anywhere. There is no, I can say that there is not a localized electron density in the case of s orbital. It is equally distributed in all the directions. But here when I talk about p, if I am talking about that this loop is having the plus phase, then obviously the electron density will be localized in this plus phase. Suppose if I am talking about this s orbital with plus phase, then obviously I have only one option, that this is the region where it will form the overlapping. Whereas in the case of s orbital, the electron density is equally distributed in all the directions. This is non-directional. Non-directional. So effective overlapping will take place in the case of p as compared to s. Okay. So please remember these points. Now you will tell me the order of strength of bond. Okay. First, 1s 1s, 2s 2s, 3s 3s. Second, 2s 2s, 2p 2p, 3s 3s. Third, 2s 2p, 2p 2p, 3s 3s, 2s 2s. Chaliye, very quickly, tell me the first one. So Reshma, can you please tell me about the first one? What is the real order? One s is more than 2s2, absolutely correct. This is the order. Shanmukha, can you please tell me the second one? Yes, can you please tell me the second one?
The 2p 2p is greater than 2s 2s greater than 3s 3s.
2p 2p greater than, just a second, 2p 2p greater than 2s 2s, absolutely correct, and it's greater than 3s 3s, absolutely correct. Ankit, can you please tell me about the third one?
Sir, 2p 2p.
Yes.
2s 2p.
Yes.
2s 2p.
2s 2s.
2s 2s.
अरे तीन इतने सारे कहाँ हैं?
3s 3s.
Yes. This is the order. This is the order. I hope this is clear. Tell me. I hope this is clear.
Yes.
Alright.
Yes, sir.
Now, so if you remember from the junior classes or from, yes, junior classes, that we say that metals, or we can say that elements having less than 4 electrons in its valence shell lose these electrons to form cations. Yes or no? To form cations. Tell me. And we say that these act as metals, because metals are the ones which undergo oxidation. We also say that elements having greater than 4 electrons in its valence shell tend to gain electrons, okay, to form anions, and they act as non-metal. Obviously they complete their octet. Now carbon is having 4 electrons in its valence shell. Tell me what it will do. Gain or lose electron? Tell me. Carbon is having 4 electrons in its valence shell. What will it do? Tell me. Yes? Tell me.
Sir, it can neither lose nor gain, sir. It will share its electrons.
So why it will neither lose nor gain? Yes, tell me. Why?
A very high amount of energy will be required in any process.
Why? And what is that energy? So obviously,
That ionization enthalpy or electron gain enthalpy.
Ionization enthalpy.
And it will be very high, right? Yes. So carbon shares its 4 electrons. Yes or no? And form covalent bond. Covalent bond. Tell me yes or no?
Yes, sir.
Okay.
Yes, sir.
Now I am writing carbon. It is 1s2, 2s2, 2p2. I am considering the valence shell. This is 2s. This is 2s. This is 2p. I have 2 electrons here. This is my ground state. So VBT says that overlapping of half-filled atomic orbitals take place to form the covalent bond. So suppose if I am talking about the formation of methane, I know that methane exists. Methane exists. Here we have 4 hydrogen attached to carbon. So how will I show the formation of, or what will pave the way for the formation of CH4? Here I have only 2 half-filled atomic orbitals. Tell me.
Sir, an electron from 2s will jump to the empty orbital of 2p.
So 2s, the electron from here will jump to here. This is what you are saying?
Yes, sir.
And this is my excited state, right? Excited state. Okay. And now 4 hydrogens, 1s of 4 hydrogens can combine with these 4 half-filled orbitals, and it will lead to the formation of CH4. Is that what you are saying? Tell me.
Yes, sir.
Okay. But I have 3 questions to you. Who is this? Shanmukha?
Yes, sir.
Shanmukha, I have 3 questions. Question number 1. Since we know that CH4 exists, then obviously it has to be formed. It has to be formed, and it has to be formed at room temperature because it exists. So, you said that this electron will get excited to the empty 2p orbital. That this 2s or electron will get excited to the empty 2p orbital, which is absolutely fine. But my first question is that will this excitation take place on its own, or you are providing some sort of energy for this to take place? First question. Second, will this excitation take place in all the molecules? Will this type of excitation will take place, will this take place in all the atoms, in all the elements to form the respective bonds? And my third question is that I'm talking about this. We know this is my 2s and this is my 2p. Just now I said that p overlapping is more than s overlapping. So obviously I have s and p and s and s. So s and p overlapping, that means s of hydrogen and p of carbon is more stronger, is more effective than s and s. So if I'm talking about CH4, then I am saying that 3 CH bond lengths should be same. 3 CH bond lengths should be same, and 1 CH bond length should be different. Yes, tell me. Bond length should be different. Should be different. But this doesn't happen. We know that all four CH bond lengths are same. So I have 3 questions. Anybody can volunteer, anybody can answer if you want to, if you know and if you want to try. My first question is that will this type of excitation take place in all the atoms, elements? My second question is that if this type of bond formation is there, then obviously 3 CH bond lengths should have been the same and 1 CH bond length should have been the different. Had this type of formation takes place, this type of bond formation takes place, right? Tell me. Tell me.
Sir, we have to provide some energy for the excitation of the electrons, sir.
Okay. What about others? Ankush, there is no point of...
Yes, sir.
Ankush, there is no point of joining the class this late. I will still mark you absent. Tell me. Yes, Ankit, tell me. So will this excitation takes place on its own, or you are providing some sort of energy for this to take place?
Sir, some energy has to be provided.
Okay, but if I am saying that CH4 exists and not in a CH4, there are many molecules which exist in at the room temperature. So who is providing energy then? And CH4 exists, are you providing energy to the methane? Yes, tell me. Or this is a spontaneous shifting, a spontaneous jump of electron that it is taking place on its own. Tell me. Yes. Who will tell me? Yes, Ankush.
Sir, as soon as any element comes near it, it will spontaneously jump into its orbital.
What is this then? At one point you are saying you are providing energy, at another point you are saying it will jump as soon as the element comes. Tell me. Okay, Ankush, but take care in future. I asked you all not to miss these classes of chemical bonding. Ankush, please make sure you won't, you attend all the classes. Alright. So see, first of all, this is a spontaneous shifting. This is a spontaneous shifting. That means this much of energy is being provided at the room temperature only. Okay? Yes, Ankit? Yes? Tell me. So,
yes,
this is your spontaneous excitation. Alright. Now, I want to talk about another molecule, and that is PCl5. So phosphorus is 1s2, 2s2, 2p, 3, 2p6, 3s2, 3p, 3. Valence shell, 3s, 3p. Right, this is my ground state. Who will account for the formation of PCl5? Tell me. Yes, tell me. Who will tell me about the formation of PCl5? PCl3 is obviously very much evident from here that 3Cl will come and make a bond with these 3 half-filled orbitals, and PCl3 is formed. What about PCl5? We know that PCl5 exists. It exists. Yes, tell me.
Sir, 1 3s electron will go into 4s.
Into 4s? First of all, not 4s, we have the empty 3d orbital here. We have the empty 3d orbital. Yes? So you are saying one of the s will jump into 3d, and this is my excited state. Yes or no? Tell me. And then I
Yes,
think
sir.
5Cl will come and form a bond. Now again I have the same question. Is this shifting if this excitation is spontaneous, natural, or you are providing some sort of energy for this to take place? Tell me. You know that it exists at room temperature. Tell me. Think about it. Yes, think about it. So see, first of all, this is not a spontaneous thing. And whenever I talk about the excitation, that please remember that whenever the electron shifts from S to P, it is spontaneous. But whenever it is from S to D and P to D, it is not at all spontaneous. Because the energy gap is high. Because the energy gap between two atoms, between S and D, is very high. Okay. Then why PCl5 exists? Tell me. Why PCl5 exists? Now this is important to understand that PCl, which is electronegative, tell me, out of
Chlorine.
Chlorine. So I am saying it is partial negative, it is partial positive. Now when it is having a partial positive, so see, earlier this is my fluorine, 3s was here, 3p was here, 3d was here. This energy gap is too high. As soon as I have a partial positive charge or a positive charge on this, S gets contracted. I mean, obviously nucleus will pull S, then we have 3p will get pulled further and 3d will pull the maximum, and this energy gap decreases. This energy gap decreases. So whenever we have an electronegative element attached, it leads to the formation of partial positive or positive charges, and due to which there is a contraction in the atomic orbitals. There is a contraction of atomic orbitals. So what is the condition? Condition is that there has to be an electronegative element attached. Now, having said that, what about pH5? Does it exist or not? Tell me. Does it exist or not?
No, sir.
So pH5 does not exist because no such excitation happens here. No such excitation can take place here. Tell me if this is clear. Tell me if this is clear.
Yes, sir.
Now my second question is, CH4, like I said, we know that and since now we have learned the VSEPR theory, so CH4 is tetrahedral. We know that all the 4 CH bonds are same. Why? Why? Tell me. Why?
Sir, maybe interelectronic repulsion.
No. VBT gives us a concept of hybridization. VBT gives us the concept of hybridization. Or you can say that in order to explain this, there is a concept which is hybridization, hypothetical concept, which means intermixing of atomic orbitals. Intermixing of atomic orbitals intermixing of, this is basically intermixing of atomic orbitals. Like for example, I have, this is 2s and this is 2p of carbon. Now what happens, this s and these p, they get intermixed to form, since 1s and 3p, that means 4 atomic orbitals are intermixing to form 4 sp3 hybridized orbitals. 4 sp3 hybridized orbitals. Like this. These are 4 sp3 hybrid orbitals. Since 4 atomic orbitals are getting intermixed, leading to the formation of 4 sp3 hybrid orbitals. Tell me if this is clear. Now why? Why is this taking place? See, I have, this is 2s, these are 3p, obviously raised in energy. Now what happens when these intermix, they form these degenerate orbitals. These are degenerate, that means all 4 are having the same energy. Here there was a difference in energy and this was the energy gap. But if you see, the energy gap has been lowered due to, energy gap is lowered due to hybridization, is lowered leading to stability. You know that when energy is decreased, leading to stability. Leading to stability. And these are degenerate hybrid orbitals. All 4 are having the same energy. So see, this is what is taking. And with these 4 hybrid orbitals, now the 1s orbital of hydrogen overlaps. Tell me if this is clear. Tell me if this is clear. Yes, tell me if this is clear. Now let's.
Sir, please explain it again.
What should I explain it again? Tell me. What haven't you understood?
Sir, why this energy gap is lowered?
This energy gap is lowered. Now there was an energy gap between 2s and 2p, but now this is lowered and all 4 are of equal energy now. Overall, the energy gap has been decreased and all 4 are of equal energies. Now since all 4 are of equal energies and the energy gap is lowered, that means stability is achieved. Stability is enhanced. And if stability has been achieved, now with these 4 atomic, these 4 hybrid orbitals, now there are these 4 hybrid orbitals which will overlap with 1s orbital of hydrogen, not the individual 2s and 2p. So basically they have intermixed, they have been intermixed together. Intermixing of s and p orbitals takes place to form hybrid orbitals. Now these hybrid orbitals are the ones which, and whose hybrid orbitals? These 4 hybrid orbitals are of carbon. So basically this is only about carbon. And if I ask you what is the hybridization of carbon in CH4, then you will say the CH4 it is sp3 hybridization. Why? Because 2s and 2p's, 3 2p's are intermixing to form 4 sp3 hybrid orbitals. Tell me if this is clear. Now you will understand it more.
Yes.
You will understand it more, just give me a second. So I am saying that I have a carbon. I am saying that it is your S. It is your S and it is your P. It is your S and it is your P. Suppose this is P. This is overlapping. This is overlapping. Well, this is getting intermixed. So what happens? This is the nucleus. This loop will increase in size. And this smaller loop is. This is my SP. If 1s and 1p is getting intermixed, then this is my 1sp, or you can say, yeah, sp hybrid orbital. This is my sp hybrid orbital. Tell me if this is clear. Because there is an overall increase in the electron density when these two are getting mixed. That means within the when they are overlapping within the same phase, intermixing within the same phase, the overall electron density increases, and I have shown it with a thicker loop. And obviously, this is the negative. The loop with the negative phase. Tell me if this is clear.
Yes, sir.
Yes? This is it.
Yes, sir.
No, it's fine. Okay. So suppose if I'm talking about CH4, suppose if I am talking about CH4, this is my C. This is my 1 sp hybrid orbitals. Okay. This is my another sp3 hybrid orbital. This is my third sp3 hybrid orbital, and this is my fourth sp3 hybrid orbital. Okay. These are my 4 sp3 hybrid orbitals of carbon. Now with these, there is 1s orbital of hydrogen, 1s orbital of hydrogen, 1s orbital of hydrogen, and here also 1s orbital of hydrogen. So this is along the internuclear axis, or this is S, so obviously S cannot form pi bond, so there is a formation of a sigma bond, sigma bond, sigma bond, and sigma bond. And with this I can say that all the 4, this is hydrogen, 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 hydrogen. And with this I can say that there is, all the CH4 bond lengths are same. Okay. And this is about CH4. Now what about C2H4, that is ethene? Suppose if I am talking about ethene, what about this? So again I have carbon. Now you will understand the things in a better way. This is 2s and I have 2. Now one carbon is forming a bond with one carbon and 2 hydrogen, just like this. Okay. And same, and there is a double bond in between. Okay, there is a double bond in between. Now according to VBT, the first bond is always the sigma bond, the second bond is always the pi bond. Please remember. Now, and also this. So if I ask you what is the hybridization of this carbon, you will say, sir, this carbon is sp2 hybridized. Why? Because I told you that while predicting the hybridization, do not consider the pi bond. Remember? Yes, tell me. Remember?
Yes, sir.
So this is my actual carbon, ground state. Then, this is the excited state of carbon. Now what happens? 1s and 2 p's get, they are intermixed together. They are intermixed together. And since 3 atomic orbitals are getting intermixed to form 3 hybrid orbitals. And what hybrid orbitals? 3 sp2 hybrid orbitals. 3 sp2 hybrid orbitals. Now one of the p is unhybridized. One of the p is unhybridized. One of the p is unhybridized. Okay. Now see what will happen. This is my one carbon. One of the sp2 hybrid orbitals of this carbon gets overlapped with one of the sp2 hybrid orbitals of another carbon. Okay, another carbon. One of the sp2 hybrid orbital of this carbon, or 2 of the sp2 hybrid orbitals of this carbon overlaps with the 1s orbital of hydrogen. Okay, this is sigma, this is sigma, this is sigma. Similarly, 2 of the sp2 hybrid orbitals of this carbon, they get overlapped with hydrogen. Alright. Now I have one unhybridized p orbital. Suppose I'm writing it like this. This is my unhybrid p orbital. Now I'm considering this to be my internuclear axis. Now, so, and I have electrons in this. I have one electron here, one electron here. So there is a lateral or sideways overlapping. There is a lateral or sideways overlapping leading to the formation of a pi. And how I will show it? I have a carbon, I have another carbon. There is a sigma bond, but there is a pi bond also, just like this, above and below. Okay, and obviously this is H. Tell me this is clear. Yes? Tell me if this is clear. Yes, tell me if this is clear.
Yes, sir.
Okay. Now, what about ethyne, acetylene? Again, 2s. In acetylene, I have 1 sigma, 2 pi's. This is also sigma, this is also sigma. If I ask you the hybridization, you will say, sir, sp hybridized. So basically 1s and 1p get intermixed to form 2 sp hybrid orbital, and 2, these are unhybridized p orbitals. These are unhybridized p orbitals. So let me show you. This is my first carbon. 1 sp hybrid orbital of this overlaps with 1 sp hybrid orbital of this. Then 1 sp hybrid orbitals of this overlaps with hydrogen. Similarly, I have this overlaps with hydrogen. Sigma, sigma, and this is also sigma. Now I have 2 unhybridized p orbitals, 1 and 2. Similarly, 1 and 2. Now, lateral overlapping. Yes, there is a formation of 2 pi bonds. There is a formation of 2 pi bonds. और इसको आप दिखाने के लिए तो ऐसे दिखा दो, क्योंकि ये दोनों पाई बॉन्ड हो गया ऐसे। Tell me if this is clear. Yes, tell me if this is clear.
Yes, sir.
Clear? Okay. Now I am giving you some molecules. You will tell me whether these molecules exist or not. ठीक है? Existence बना. First, BF3. Very quickly.
Yes, sir.
Okay. BH3. Very quickly.
No, sir.
अरे चलो इसको हटा देते हैं, वैसे it exists in the form of a dimer, but I'm not talking about it as of now. What about BF4 negative? Tell me, BF4 negative. BF4 negative. Tell me. This is boron.
No, sir.
This is boron. In boron, I have 2s and 2p1. So after excitation, this is my thing. So 1f, 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 and 1f negative can donate its electron in the empty orbital. So yes, it exists. Yes, Ankit, it exists. Similarly, BH4 negative, it exists. BCl3, obviously it exists. BCl3 negative, tell me. BCl4 negative, tell me.
Yes, sir.
BCl4 negative, tell me. Now it doesn't exist because small boron can accommodate 4 smaller fluoride surrounding it, but it cannot accommodate the larger chloride around it. I hope this is clear. You have to consider the size also. Fluorine belongs to the same period, and it is smaller size. So a small boron can accommodate 4 fluorine around itself, but it cannot accommodate the larger chloride around itself. Okay? Alright. Tell me about this. Tell me about this.
No, sir.
No, when it cannot, I mean when BCl4 cannot exist, so it will definitely not exist. Alright. AlCl4 negative, tell me.
Yes, sir.
It exists, yes, because aluminium is larger in size, so it can accommodate 4 chloride. AlF6 2 negative, tell me very quickly, or 3 negative. Tell me.
Yes, sir.
It exists. AlCl6 3 negative.
Yes, sir.
It doesn't exist. I mean, it can accommodate 4 chlorine, but cannot accommodate 6 chloride. Okay, 6 chlorine. Then next, silicon. Okay, carbon. CF. Just a second. CF6 2 negative. Tell me.
No, sir.
Yes, sir.
It cannot exist. Carbon cannot form more than 4 bonds. The covalency is 4. Because you know why, Shanmuka? Because even if you are talking about the excitation, more of excitation, because even after excitation you are getting 2s and 2p's. Because there is no 2d. Yes? So how can it accommodate 6? It can only accommodate 4. In the case of aluminium, there is a possibility for the accommodation of 6 because there is an empty 3d in case of aluminium. So first of all, you have to check for the availability of an empty orbital. Suppose if you are not having an empty orbital, then obviously you can't be talking about the excitation. Yes? And suppose if you are having an empty orbital, then you will check for size. Then you will check for size or steric clouding. Okay. What about SiCl4? Tell me very quickly.
Yes, sir.
Yes, sir.
It exists. SiCl6 2 negative. Oh, sorry. SiF6 2 negative. Tell me. Yes, it exists.
Yes, sir.
Yes, sir.
SiCl6 2 negative. Yes, tell me.
No, sir.
No? Okay. SiCl6, no. Yes, because it cannot accommodate to others. SiBr6 2 negative.
No, sir.
No. Alright. Let's say for example, if I talk about nitrogen. Nitrogen is 1s2, 2s2, 2p3. So this is 2s and this is 2. Now obviously you won't be talking about excitation because there is no 2d available. So can you please tell me how many bonds can nitrogen form? Like maximum bonds that nitrogen can form. Maximum number of bonds.
4.
Yes, maximum number of bonds, not 5, please. No, maximum number of bonds formed by nitrogen is 4. 1 by coordinate and 3 coordinate. Okay, next. Alright. What next? So, this we have discussed. Resistance. And other hybridizations we have already seen in the case of VSEPR theory. sp3d, sp3d2. Okay. Now, let us discuss molecular orbital theory. First of all, VBT or VSEPR theory both considers, both accounts for the valence shell electrons. But MOT says that all the electrons, whether valence shell or inner shell electrons, they have some role to play in the formation of a molecule. I hope this is clear what I'm trying to say. Tell me. All the electrons, whether valence shell or inner shell, they have some role to play in the formation of a particular molecule. Alright.
Yes.
Take care. So, it considers all the electrons. Considers total electron count. It considers total electron count, not the valence electron count. Okay. Secondly, for example, we talked about C2H4 and I said this is the thing. According to VBT, C2H4 is this, where I have 1 sigma, 1 pi. Now suppose if I talk about C2 molecule, only C2 molecule, then obviously you will say, sir, C2 molecule will look like this. Yes, tell me, yes or no? Because obviously when there is a double bond, there should also be a double bond just like this. Yes or no? And there should also,
no, sir.
And here also there should be a sigma bond and there should be a pi bond. There should be a sigma bond and there should be a pi bond according to VBT. But this doesn't happen. What happens? We have a double bond, but both the bonds are pi bonds. There is no sigma bonds. This is MOT. And this is true also. Both are pi bonds. According to VBT, one bond has to, because according to VBT, like I said, it says that the first bond is always sigma and the second bond is always pi. But here, there is no sigma bond. Then this is also a limitation of VBT. Tell me, yes or no? And VBT does not talk about the bond order, it does not talk about the magnetic nature, whether it is paramagnetic, whether it is diamagnetic, how many unpaired electrons are there, and it doesn't talk about the bond order, yes, bond length, nothing. So because of that, we are moving to another theory, and that is molecular orbital theory. And that is molecular orbital theory. Okay. Now when I talk about MOT, we will be doing 3 things. Number 1, we will be seeing the mixing of atomic orbitals. Okay. But not by the principle of hybridization. MOT does not use that word. It is by LACO. The principle is LACO. LACO is linear combination of atomic orbitals. Linear combination of atomic orbitals. Linear combination of atomic orbitals. Number 1. Number 2, formation of molecular orbital diagrams, or you can say MO diagrams. MO diagrams. What we call MODs. And the third step we will be doing is filling of these MODs. In accordance to of Bohr principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. Tell me if this is clear. This is how we will do. So this is a scheme, what we are going to do in the molecular orbital theory. First we will see the mixing of atomic orbitals, then the formation of molecular orbital diagrams, and finally the filling of MODs in accordance with of Bohr principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. Tell me if this is clear.
Yes, sir.
Clear? Alright. Now see, if you remember I told you that electron in an atomic orbital is associated with a wave. Remember? Electron in an atomic orbital is associated with a wave. Yes or no?
Yes, sir.
So suppose if I am talking about 1s, this is my atom A, this is my atom A, and this is my another atom A, this is my another atom. I am talking about 2s, suppose I am talking about 2s. This is also 2s. So can I say this is also associated with the wave? Like this. Suppose I am talking of this as plus phase and this is also plus phase. I am considering this to be a plus phase. This is my nucleus. This nucleus. And this is the same diagram. I suppose if I am drawing it psi, because every wave is associated with a wave function. So this is psi, and this is the same. That electron density near the nucleus is maximum, and then it goes on decreasing. Same goes for this. Take it. Now, so when these two waves intermix, it's a process called interference. So we have interference. That is, interference is the intermixing of waves. Interference is basically intermixing of waves. Now, we can have two types of interference. One is constructive, another is destructive. Let us talk about the constructive interference first. So this is basically the constructive interference, then they are in the same phase. So what I am getting is, this is my nucleus 2, this is my nucleus 1, this is R, this is what I will get. Tell me yes or no? Yes, and this is psi. This is R. Is it clear? Tell me. This is my constructive interference when they are in the same phase. Okay. But like I said, if you remember that psi is not having any physical significance. Ankit, if psi is not having any physical significance, what we do? Yes? Ankit. Shalukha.
Yes, sir.
Tell me, what we do? If psi is not having any physical significance, we square it and we say that this particular thing talks about the probability density. Probability density. So the same graph I can draw like this, the same curve. The overall amplitude increases, and this is what I get. Yes or no? Tell me, Ankit, Sheetal.
Yes, sir.
Yes? Now what is this region? This is basically the internuclear region. Internuclear region. Internuclear region. Now, so when two waves mixed constructively, then what happens? The overall electron density in the internuclear region increases. And if the electron density is increasing, can I say that the attractions between the nuclei and this electron density increases? Yes or no? Tell me. The attractions.
Yes, sir.
Attractions between the nuclei, two nucleus. First one is of atom A, and this is for another atom A. So between nuclei and electron increases. And you know that whenever the attractions increases, what happens? Energy is released. And this is the condition of bond formation. And I am saying that when two waves or two atomic orbitals, they are mixed constructively, then it leads to the formation of bonding molecular orbital. Tell me if this is clear. Yes, tell me if this is clear. Okay, so what I said is, I have an atomic orbital of A, of the first A. I have the atomic orbital of the second A. They get intermixed to form, first of all, since two atomic orbitals are getting intermixed, they will form two molecular orbitals. So this is of A, this is for A. This is also for A, right? And this is for A2 molecule. So I am saying that suppose if this is 2s and this is 2s, then I will get two of the molecular orbitals. One is decreased in energy, that means one is stabilized by some amount of energy, and the other is destabilized by the same amount of energy. So this is called, the one which is lower in energy is bonding molecular orbital, and the one which is raised in energy is anti-bonding molecular orbital. Tell me if this is clear. Yes, tell me if this is clear. So bonding molecular orbital, I have already shown how these atomic orbital leads to the formation of the bonding molecular orbital when they are mixed constructively. Now we will discuss the formation of anti-bonding molecular orbital in the next class, and I will show you why the overall electron density in the internuclear region decreases in the case of anti-bonding molecular orbitals. Okay? I hope this is clear. Tell me. Alright. Okay, so stopping it here. We'll continue from here in the next class. Okay?